On a Monday evening in May, a research truck bristling with radar equipment parked itself directly in the path of the most violent wind ever measured on planet Earth. And what it recorded that night rewrote the rulebook for an entire branch of science. This isn't a legend passed around by storm chasers. This is a documented, peer-reviewed measurement that still stands unbroken more than 2 decades later. And by the end of this video, you're going to understand exactly how one tornado on one evening in one small stretch of Oklahoma permanently changed how humanity studies, predicts, and survives the most violent storms on the planet. Think about that for a second before we even get into the details. Every field of science has a handful of moments where the data collected from one single event ends up rewriting the textbooks for everyone who comes after. Astronomy has its supernovae, seismology has its megaquakes, and tornado science has this one specific evening in Oklahoma, a night that meteorologists, storm chasers, and severe weather researchers still reference as the moment their entire discipline shifted from educated guesswork toward genuine, real-time measurement. The date was May 3, 1999. The place was central Oklahoma, just southwest of Oklahoma City. A supercell thunderstorm had been building through the afternoon, feeding off a textbook collision between a powerful low-pressure system and thick, humid air pulled up from the Gulf of Mexico, the exact kind of atmospheric setup that meteorologists watch for with genuine dread. Around 6:23 in the evening, the 9th tornado to drop from that same supercell touched down near the small town of Amber. Within minutes, it had grown into a mile-wide wedge tornado, one of the most terrifying shapes a tornado can take. And it began a slow, deliberate crawl toward Bridge Creek, then Newcastle, then straight into the southern edge of Oklahoma City itself, and finally into the city of Moore. Here's what makes this moment different from every other devastating tornado in the historical record. Waiting nearby was a team from the University of Oklahoma, led by a researcher named Josh Wurman, operating a piece of equipment that barely existed anywhere else on the planet at the time. It was called a Doppler on wheels, a mobile radar truck built specifically to chase down tornadoes and scan inside them at close range, something fixed weather station radars simply could not do. Wurman hadn't built this technology overnight. He'd spent years developing the concept specifically because he recognized a massive blind spot in severe weather science. Fixed, permanent Doppler radar stations, the kind used by national weather services, are incredibly good at spotting rotation inside a distant thunderstorm and issuing a warning. What they cannot do is get close enough or scan fast enough to actually resolve the fine, violent detail happening inside a tornado's core as it's tearing across the ground. Wurman's answer was to essentially strap a research-grade Doppler radar onto a truck chassis and drive it toward the storm instead of waiting for the storm to pass a fixed antenna. The first working version of this system had already proven itself useful during an earlier tornado research campaign in the mid-1990s, but nothing in those earlier deployments prepared the team for what they were about to encounter in central Oklahoma in 1999. As the tornado reached peak intensity near Bridge Creek, the Dow crew got their radar beam directly into the heart of the vortex, roughly 100 to 200 feet above the ground. And what came back on their screens was a number that, at first, looked like an equipment malfunction: 301 miles per hour, plus or minus 20. Some analyses of the same dataset later pushed the estimate even higher, up toward 321 miles per hour. To put that number into perspective, a Category 5 hurricane, the most violent storm classification that exists for tropical cyclones, only needs sustained winds of 157 miles per hour to earn that label. This tornado was moving air at nearly double that speed, concentrated into a rotating column that at times stretched close to a mile wide. It remains to this day the highest wind speed ever measured in Earth's atmosphere by any instrument, anywhere, in any storm. And I want to pause on something important here because getting this right matters more than making it sound dramatic The National Weather Service does not officially certify this number as a record. The measurement was taken well above the surface, where friction with the ground naturally slows wind down, and there's inherent uncertainty in any radar-based wind estimate, especially one made in real time against an environment already trying to tear the recording equipment apart. So when you see this number cited as a world record, know that the honest, complete version of that claim is this. It is the highest wind speed ever reliably measured inside a tornado by mobile Doppler radar. And among the scientists who study these storms for a living, it remains the benchmark every other extreme tornado gets compared against. Before we go further, tell me something in the comments. Had you ever heard that a single storm broke a wind speed record that still stands over 2 decades later? And if you lived anywhere near Oklahoma City in 1999, I want to hear what that evening was actually like for you, because the survivor accounts from this specific storm are some of the most detailed on record, and I'd genuinely like to know if your memory lines up with what the data shows. Now let's talk about what this tornado actually did on the ground, because the science side of this story doesn't erase the human cost, and it shouldn't. The tornado stayed on the ground for roughly 85 minutes and carved a track nearly 38 miles long, one of the longest, most sustained violent tornado tracks ever documented in a major metropolitan area. It reached F5 intensity, the highest possible rating on the original Fujita scale in use at the time, and it held that extreme intensity across multiple separate strikes as it moved through Bridge Creek and then again through sections of Moore. 36 people were killed directly, with 5 additional deaths tied to the storm indirectly, and nearly 600 people were injured. Almost 1,800 homes were completely destroyed, with another 2,500 damaged, and total damage reached roughly $1 billion in 1999 money, making it, at the time, one of the costliest tornadoes ever recorded in United States history. This was not an abstract data point sitting in a research paper. This was one of the deadliest, most expensive tornado disasters modern Oklahoma had ever experienced, unfolding in real time in front of live television cameras across the entire metro area. It's also worth understanding that this tornado wasn't operating in isolation. It was the most destructive member of a much larger historic tornado outbreak that swept across central Oklahoma and neighboring states that same evening. Other significant tornadoes touched down that day near Choctaw, Del City, Midwest City, Stroud, Dover, Mulhall, and Cimarron City, part of a single outbreak that produced 50 confirmed fatalities across the region and left nearly 900 people injured, with combined damage estimates exceeding $1.5 billion. Researchers studying supercell behavior that day had, in effect, an entire laboratory of tornadic storms unfolding simultaneously across a wide swath of the state, giving meteorologists a rare large-scale opportunity to compare how different tornadoes spawned from different supercells behaved under nearly identical, broader atmospheric conditions on the very same afternoon. And that's actually part of what makes this event so pivotal, because of how it was covered as it happened. Local meteorologist Gary England, anchoring continuous coverage for Oklahoma City's KWTV News 9, is widely credited with saving hundreds of lives that evening through his moment-by-moment tracking and blunt, urgent on-air warnings as the tornado bore down on specific neighborhoods. The National Weather Service office in Norman issued its tornado warning for the Bridge Creek area with roughly 13 minutes of lead time before the tornado arrived, and residents in Moore had well over 30 minutes of continuous, escalating warning before the storm reached them. This event was also significant enough that it prompted the first-ever use of what's now called a tornado emergency statement, a specific, more urgent tier of warning language the National Weather Service created because standard tornado warnings weren't conveying the true severity of what was bearing down on the city. That single addition to the warning vocabulary is still in use today, issued only for tornadoes posing a severe, imminent threat to human life in densely populated areas. But before we get to the labs and the research papers, it's worth understanding just how deeply this single evening reshaped everyday life across central Oklahoma. Because the scientific ripple effects and the practical on-the-ground changes happened almost side by side. In the years immediately following this tornado, the region saw a surge in the construction of underground and above-ground storm shelters, often called safe rooms, in both private homes and public buildings including schools. Building codes in tornado-prone parts of Oklahoma were revisited with new urgency, informed directly by damage patterns documented from this storm. Emergency management agencies used the storm as a case study for coordinating evacuation and shelter guidance, and local television stations across Tornado Alley studied Gary England's live coverage of the event as a model for how urgent, specific, life-saving communication should actually sound in the moments before a violent tornado strikes a populated area. None of that infrastructure and protocol exists in a vacuum. It exists because this specific storm proved, in the most brutal way possible, exactly what was at stake when a violent tornado meets a major metropolitan area. So here's where the science part of this story really begins, because a wind speed record by itself, however extreme, doesn't automatically change an entire field. What changed tornado science was everything this event allowed researchers to actually see for the first time. Before mobile Doppler radar existed, scientists studying tornadoes were largely limited to post-storm damage surveys, walking through wreckage afterward and estimating wind speeds based on what got destroyed and how. That approach, useful as it was, meant tornado science was essentially forensic. Researchers were always reconstructing an event after the fact, never observing the actual wind field while the tornado was alive and raging. The Doppler on Wheels program, which Werman had spent years developing specifically to solve this problem, changed that completely. For the first time, researchers could drive a radar system close enough to a live violent tornado to measure its internal wind structure directly, in real time, while the storm was still on the ground. The Bridge Creek Moore data didn't just hand scientists one dramatic number. It gave them an extraordinarily detailed look at how wind speed is actually distributed inside a violent tornado, how it varies with height above the ground, and how concentrated the most extreme winds really are within a relatively narrow band of the vortex. That kind of high-resolution internal wind data was essentially unprecedented at the time, and it became a foundational reference point for the researchers who spent the following years reworking how tornado intensity itself gets classified. One of the most important discoveries buried inside that data was something researchers had suspected for years, but rarely had the instrumentation to prove conclusively. Violent tornadoes often aren't a single, smoothly rotating column of wind. They can contain what scientists call multiple vortices, smaller, intensely violent subvortices that orbit within the larger tornado circulation like miniature tornadoes riding inside a bigger one. Each of these subvortices can carry its own localized wind maximum, sometimes even more extreme than the surrounding parent tornado, and they can appear and dissolve within seconds as they rotate through the circulation. Before mobile radar could scan a live tornado's internal structure, this phenomenon was mostly inferred from damage patterns, oddly narrow bands of extreme destruction running through otherwise moderate damage zones. The 1999 data gave researchers direct radar confirmation of exactly this structure in action, and it fundamentally changed how scientists think about where a tornado's most dangerous winds are actually located at any given moment. It's not always the center of the funnel. Sometimes it's a fast-moving subvortex that might pass over one house and completely spare the house next door, which also happens to explain something storm survivors have described for generations: that strange, almost random pattern where one home is reduced to a bare concrete slab, while a neighboring structure is left standing with comparatively minor damage. That reworking effort had a name, and it directly traces back to data collected in events like this one. The original Fujita scale, created back in 1971, estimated tornado wind speeds almost entirely from damage to structures, using assumptions about how much wind it takes to flatten a house or snap a tree that hadn't been rigorously tested against real measured wind data. Researchers increasingly understood that those original assumptions were producing wind speed estimates that ran too high for the damage actually being observed. Using data gathered from events like Bridge Creek Moor, alongside engineering studies of how buildings actually fail under wind load, meteorologists and wind engineers spent years developing a replacement framework. In 2007, that work became official with the introduction of the enhanced Fujita scale, a significantly more precise system that ties specific types of damage to 28 different kinds of structures and vegetation, to far more realistic wind speed ranges. Every tornado rated in the United States since 2007 has been measured against this revised scale, and its accuracy owes a direct debt to the internal tornado wind data that events like this one made possible for the first time. The impact didn't stop with the rating scale. This event became one of the central case studies behind an entirely new era of coordinated tornado field research. In the years that followed, government-funded research campaigns dramatically expanded the use of mobile radar in active tornado environments, deploying fleets of radar trucks, weather balloons, and instrumented vehicles directly into Tornado Alley to gather exactly this kind of close-range data across dozens of storms, rather than relying on a single, once-in-a-generation event. The largest of these efforts eventually grew to include more than 50 specialized vehicles and over 100 scientists and crew members working together across an entire storm season, deploying multiple radar trucks simultaneously around the same tornado to build a three-dimensional picture of its wind field from several angles at once, something that would have been technically impossible before the original Dow proved the concept was viable. Some of these teams went on to develop armored vehicles specifically designed to be driven directly into a tornado's path, carrying instruments capable of surviving direct impact from the vortex itself. An idea that would have sounded like science fiction before 1999 proved that close-range tornado data was actually possible to collect and survive. This data also fed directly into how warning systems themselves evolved. Understanding that a tornado's most violent winds can be concentrated in a narrow, rapidly shifting core, sometimes with multiple smaller vortices rotating within the larger one, helped forecasters and researchers refine exactly how much lead time is realistically achievable before a violent tornado strikes, and how warning language needs to communicate genuinely life-threatening intensity versus a more routine tornado threat. That distinction, the difference between a standard warning and a tornado emergency, exists in its current form because of lessons learned directly from this event and the ones that followed it. There's also a longer, more sobering thread to this story because the same stretch of Oklahoma got hit again. In 2013, a tornado struck an overlapping area of the Oklahoma City metro, producing winds estimated near 210 miles per hour and growing to over a mile wide, killing 24 people and causing roughly $2 billion in damage. That event reaffirmed something researchers already suspected from the 1999 data, that this specific stretch of central Oklahoma sits in one of the most tornado-vulnerable geographic corridors on the planet, where atmospheric conditions repeatedly align to produce violent, long-track tornadoes capable of tearing through populated areas. And just a few weeks after that, in May of 2013, a separate tornado near El Reno, Oklahoma became the widest tornado ever recorded, over 2.5 miles across at its peak, with radar-measured winds again approaching the extreme range first documented back in 1999. That storm tragically killed several experienced storm chasers and researchers who had spent years studying exactly these kinds of violent multi-vortex tornadoes. A stark reminder that even with decades of accumulated data and improved instrumentation, these storms remain capable of outmaneuvering the very scientists working to understand them. Here is the perspective I want you to leave with. Tornado science before 1999 was largely a science of aftermath, of walking through wreckage and working backward toward an estimate. The measurement recorded that evening near Bridge Creek didn't just set a record number that still stands today. It proved that direct, real-time observation of a live, violent tornado's internal wind structure was actually achievable, survivable, and repeatable. That proof reshaped how tornado intensity gets classified, how warnings get worded, how field research campaigns get designed, and ultimately, how much warning time families across tornado-prone regions get before the next violent storm arrives. It's worth remembering just how young this entire scientific approach still is. Meteorologists have been trying to understand tornadoes for well over a century, but genuinely direct close-range measurement of a violent tornado's internal wind field has only existed for a few decades, and the event we've spent this entire video breaking down sits right near the very beginning of that timeline. Every improvement in tornado warning lead time since then, every refinement to the enhanced Fujita scale, every safe room built to a more rigorous engineering standard, and every storm-chasing research vehicle designed to survive a direct hit. All of it traces back through a chain of scientific progress that starts with a radar truck parked outside Bridge Creek, Oklahoma, on an ordinary Monday evening in May. 36 families lost someone that evening in Oklahoma. The science that came out of that same storm has gone on to help protect an untold number of families since, and that dual legacy, tragedy on one side and lasting scientific advancement on the other, is exactly why meteorologists still bring this storm up more than 2 decades later. If this gave you a clearer picture of how one storm reshaped an entire field of science, hit like subscribe for more deep dives into the events that quietly changed how we understand the natural world. And let me know in the comments which extreme weather event you want covered next. Stay curious, stay weather aware, and I'll see you in the next one.